This video, we will talk about exponential and logarithmic functions. So exponential function, the definition of it you will have a base and your actual variable will be the exponent. So that's why we have f of x is equal to b to the x, where b is going to be a positive constant other than 1, and then x is going to be any real number. So if we want to graph an exponential function, let's say if we have f of x is equal to 2 to the x, not 2x, but 2 to the x power, we create our chart. And I'm going to start with my positive values first, just to make sure we're okay with the exponential process. So if I put 3 in there, it's 2 to the third power. 2 times itself 3 times will give you 8. 2 to the second power is 4. 2 to the first power is 2. Don't forget anything to the 0 power is 1. Now, when you put in a negative exponent, don't forget, in order to turn it positive, you drop it down into your denominator. So that will be 1 over 2 to the first power, which is just 1 over 2. Then here, 1 over 2 to the second power, which would be 1/4, and then 1 over 2 to the third power, which would be 1/8. So if you were to graph that, you will get this shape for your function, for your graphical representation of your function. So your exponential functions will have this type of representation no matter what your translations or your shifts are, whether it be up or down, left or right, or if you were to reflect it, it will still have this general shape. So when you go about your graphs, just make sure you pay attention to your translations. This shape still should hold true. And notice how it grows, and that's where you get the term growing exponentially. It grows quick. It goes from 1, 2, 4, 8, just that quick, just off of the third movement in your X. So pay attention to your shifts and your translations. The next thing in this section, outside of the graphs, they talk about your compound interest formulas. So for in compounding periods, we're talking about in banking, money being compounded, interest being added, and so forth. We have P times 1 plus R over N to the N times T power. And then for continuous compounding, not daily compounding, but continuous compounding, we have a different formula altogether when we have P times E to the RT. So the representation of these variables, A is going to be the future value that's going to be in your account after T years. P is your principal, which is the initial deposit or loan. R is your rate. Don't forget to convert that to decimal before you put it into your formula. And then, like I said, time. T is your time, and it should be in years. Notice in your continuous compounding, we have E that is not a variable. That's actually a natural base function or exponential function, natural base E. So E to the first power is actually a value. That's 2.71828 on to infinity. So we're not going to substitute any value for E. E already has a value. You're going to raise R times T as the exponent of that E. So just make sure we're okay with the time being converted to years. If we had 24 months, we know that's 2 years. The way we would calculate, though, we would divide that 24 by 12 because it's 12 months in a year. So that means if I had 13 months, I would do the same, keep that same process or the thought process. That would be 13 over 12. If I had 17 weeks, I would put that 17 over 52 because there are 52 weeks in a year. But if I were dealing with days, I would do 137 over 360 because of Banker's rule. They don't use 365, they actually use 360. All right. Compounding periods. So if you're talking about annually, N is equal to 1. Semi-annually, N is equal to 2. Quarterly, N is equal to 4. Monthly, N is equal to 12. Daily, N is equal to 365. So quick example of that, you decide to invest $8,000 for 6 years, and you have a choice between 2 accounts. The first pays 7% per year, compounded monthly. The second pays 6.85% per year, compounded continuously, which is the better investment. So we'll look at both of them individually. First account, $8,000, 6 years, 7%. So we convert that to 0.07. Compounded monthly, so that's 12 for N. Plug it into your formula properly, 8,000 for P, 1 plus 0.07 over 12, raised to the 12 times 6 power. Once you throw that in the calculator, you get 12,160.84, 84 cents. Second account, once again, we have $8,000 for 6 years. This time your rate is at 0.0685, but we're continuously compounding. So we're using a different formula altogether. That's going to be P times E to the RT, 8,000 times E to the 0.0685 times 6. So you can put it in the calculator just like this. If you have the capability of your calculator. If not, you have to perform order of operations. Same thing with this one in the first account. You can put it in the calculator just like this, or make sure you perform the order of operations properly in order to be able to calculate. So this one with the continuous compounding will give us the value of 12,066.60. So we see the better investment is in the first account, compounded monthly. Next section talks about logarithmic functions. So start here. If for all of your x being positive, that's greater than 0, and b being positive but not equal to 1, y is going to be equal to log base b of x. And that's going to be equivalent to b to the y equal to x. So in other words, we're going to have a logarithmic form and an exponential form that's equivalent, that has the equivalent relationship. So f of x is equal to log base b of x. That's your logarithmic function there. So when you're talking about your log form versus your exponential form, y equal to log base b of x is your log form. If you want to convert it to your exponential form, notice your base is always going to be the same. So it's either the base of your log or the base of your exponent. That's going to stay the same. Here I have y log base b of x. Notice that in my logarithmic form, the x is next to the b, but in my exponential form, the y is the exponent of my b. So that's the way I look at it, is whatever's next to the b in one form should not be next to the b or the base in the second form. So once again, y is equal to log base b of x. The next one, b to the y power is equal to x. So whatever's next to your base in one form will not be next to the base in the other form. Let's look at going back and forth with those forms. So I have log form in this first set of examples, and I will convert them to exponential. So I have 2 equal to log base 5 of x. I start with 5 as my base. If x is next to 5 in my log form, then 2 is going to be the exponent of my base in the exponential form. So that's 5 squared, and then that's equal to x. The other one will be on the other side. Same thing here, 3 equal to log base b of 64. So b is my base raised to the third power equal to 64. Next one, log base 3 of 7 is equal to y. My base is 3 raised to the y power equal to 7. Next one, I'm going from log form, going from exponential form to log form. I have 12 squared equal to x. So I start off with log base 12, then it's of x equal to 2. Once again, what's next to the 12 in my exponential form should not be next to the 12 in my log form. So b cubed equal to 8, that's log base b of 8 equal to 3. Then e to the y equal to 9, that's log base e of 9 equal to y. All right, going through the properties. Our common log is log base 10 of x. So when you don't see anything there at all, they assume you know there's a 10 there. That's the log that's in your calculator. Log base 10 of x, that's your common log. When there's nothing there, they assume you know there's a 10. So log of 1, log of any log of 1 will give you 0. Log of 10 is equal to 1. Log of 10 to the x. The base of 10 and the 10 cancels, leaving you with just x. Same thing happens in the rule 2. The base of 10, log 10, cancels and leave you with the power of 1. And then here, if I have 10 raised to the log of x is your exponent. The log base 10 and the 10, once again, cancels, leaving you with just the x. Same thing happens in the natural log. Your natural log is log base e of x, and that's ln of x. That's in your calculator as well, scientific calculator as well. Log base e of x is the same thing as natural log x. They assume you know when you see ln of x, that's the base of e. So natural log of 1 is equal to 0. Natural log of e, remember this is natural log of e to the first power. When you don't see anything, it's just going to cancel out and give you 1. Natural log of e to the x cancels out, leave you with just x. Then e to the natural log of x cancels out and just leave you with x as well. So generically, when you look at these properties, log base b of 1 is always going to be 0. Log base b of b is 1. Log base b of b to the x is going to be x. And b to the log base b of x will be x. So these will cancel out, leaving you with just x. So let's put that to work. Log base 4 is 16. If I can convert this 16 into something that base 4, that will help me to be able to cancel out. 16 is 4 squared. So log base 4 or 4 squared is just 2. 8 to the log base 8 of 19, that cancels out, leaving with just 19. Here, I have to be able to represent this square root of 7 in such a way that I will just have an exponent that would be left and a base of 7. So this log base 7, square root of 7 is the same thing as 7 to the 1/2. So log base 7 of 7 to the 1/2 cancels, leaving you with just 1/2. So don't forget, square root is 1/2 as an exponent, cube root is 1/3 as an exponent, fourth root is 1/4 as an exponent, and so on. This next one, log base 81 of 1 over 9. So I need to be able to represent this 9 as 81. Don't forget, 9 is the square root of 81. So I can rewrite that 9 as square root of 81. Also, I just finished mentioning that square root of 81 is 81 to the 1/2. And then don't forget, we talked about how if it's a negative exponent, you make it positive, bring it down bottom. But if it's bottom and you want to bring it up top, that turns it negative. So there's log base 81 of 81 to the negative 1/2. So the log base 81 and the 81 cancels, leaving you with just negative 1/2 as a final answer. Log base 5 of 1 is just 0. Any log with any base of 1 would be 0. Log of 1,000, don't forget that base is 10. So convert that 1,000 to 10 to the third power. So this log of 10 to the third power will cancel, leaving you with just 3. Natural log of 1 over e to the 7. E is the key here. That natural log is base e. So that's natural log of e to the negative 7. And that cancels out, leaving you with just negative 7. E to the natural log of 7x squared. E and the natural log cancels, leaving you with just 7x squared. Final two, natural log of e is just 1. Then log base 25 of 25, once again, is just 1. Let me know if you have any questions on anything that I've said.